Hello, everyone. My name is Robert Ciotti.
And my name is Simone Williams, and we worked with Dr. Nima Rabar and WPI of Civil and Environmental Engineering on the bioinspired design of novel reinforced concrete elements.
We'll open by exploring our primary objective for our research. The goal was to develop a cement composite structure out of metallic foams and fibers with cement to create a stronger and more ductile material than traditional reinforced concrete. Now, despite concrete's saturation of the building industry, there still exist many primary concerns when using reinforced concrete for structural purposes, including rust, expansion, and moisture cracking. Now, our goal was to draw from microdesigns found in nature, like wood, bones, and sea sponges, to create a foam composite out of stronger materials, such as aluminum and steel, with cement to produce a more effective design. This design was also explored with metallic fibers, which have superior mechanical properties, including high thermal conductivity and corrosion resistance. All of this would be used in order to create a superior composite material to be used in reinforced concrete applications.
To make this new composite material, we reinforced 1-inch cement paste cubes with stainless steel fibers and 10, 20, and 40 pores per inch aluminum foam. Control samples were also made for comparisons. All of these samples had a water to cement ratio of 50% and were cured for 14 days before being tested in compression on an Instron machine in WPI Structures Lab. The image on the left shows what the samples looked like when they were in the testing machine. The control and steel fiber samples were tested until failure, and the aluminum foam samples were tested until compressed by 75%.
The results we gathered from this testing are graphed in these figures on the screen. So out of our composite materials, the strongest one performed was the steel fiber composites, which performed to a maximum compressive strength of 2,900 pounds per square inch. And the strongest foam composite was the 10 pores per square inch foam, which performed to a degree of 2,568 pounds per square inch. Both of these measurements were comparable but slightly weaker than the control sample, which was just a traditional cement. And you can see on the right figure that the 10 PPI samples performed significantly better than the 20 and 40 PPI samples. The benefit that the composites had towards the control samples was their ability to not reach a failure point, which will be elaborated on more in the conclusion.
So based on these results, we conducted calculations on a column within a simple 3-story building that was reinforced with the 10 pores per inch aluminum foam, and then one that was traditionally reinforced with rebar. Based on the calculations, the aluminum foam reinforcement was able to withstand 41% of the load the column was subjected to, while the steel reinforcement was only able to withstand or carry 18% of the load, which means that the aluminum foam reinforcement can carry about 3 times more of the load subjected on a column than traditional steel. Based on these findings, the aluminum foam composites were not able to reach a failure point, but they were able to have a maximum compressive strength and a yield compressive strength. Of the 3 aluminum foam samples, the 10 pores per inch foam sample performed the best, having an average yield strength of 3,363 psi. The steel fiber reinforced composite samples failed due to cracking, but also exhibited a good average yield stress compared to the foams. Based on the results for the foams and the fibers, further research is encouraged so that we can explore the ideal porosity, material, and microdesign to be used in reinforced concrete structures.
Thank you all so much for coming today. We are very excited to share our research, and we appreciate your consideration.